This is question 7 from paper 3 of the sample assessment materials. It's the second mechanics question. And the question says there's a rough plane inclined to the horizontal at angle alpha, where tan alpha equals 3/4. So we'll deal with that in a minute. A particle of mass m is placed on the plane and projected up a line of the greatest slope of the plane. The coefficient of friction between the particle and the plane is mu. It has constant deceleration, 4/5 g. Find the value of mu. So the first thing we need to do is draw a diagram to show all of this information. So I've got my inclined plane at angle alpha, and the question told me that tan alpha was equal to 3/4. So it's going to be useful later in the question to have values for sine alpha and cos alpha. So you can either work them out with your calculator, or you could draw a little right angled triangle. So if that's alpha, then the opposite over the adjacent is 3/4. So that side must be 5 because it's a Pythagorean triple. And then I can use trigonometry to get that sine alpha is equal to 3/5, opposite over hypotenuse, and cos alpha is equal to 4/5, adjacent over hypotenuse. Now let's put everything onto our diagram. So there's a particle with mass m. So mg is going to be acting down there. There's the coefficient of friction between the particle and the plane is mu. Now the particle has been projected upwards, so friction is going to be at its maximum and it's going to be acting down the slope and slowing it down. So friction is going to be at its maximum, it's going to be mu r. There's also a normal reaction between the plane and the particle. And the deceleration of the particle is 4/5 g. Now, the whole way through this question, for part A, the direction of motion is upwards. So I'm going to take that as positive throughout the question. So that means that the acceleration is negative 4/5 g, because it's slowing down. Now we're going to resolve our forces in order to find mu. So I'm going to be thinking in terms of parallel and perpendicular to the plane. So this force here and this force here are already perpendicular and parallel. So I need to split this one up into its parallel and perpendicular components. So it's going to be perpendicular like that and parallel like that. Now if that angle's alpha, that angle's also alpha. And this component will be mg cos alpha, and this component would be mg sine alpha. So let's start off by resolving perpendicular to the plane. So because it's in equilibrium, this would be equal to this. So R is equal to mg cos alpha. And I know that cos alpha is 4/5. So R is equal to 4/5 mg. Now, in order to find mu, I'm going to need to think in terms of parallel forces to the plane. So I know that F equals ma. So the resultant force is equal to the mass times the acceleration. So earlier on I said I was going to take that direction as positive. So the resultant force the only parallel to the plane forces that I've got are this one acting down here, mu r, and this one acting down here, mg sine alpha. And they're going to be negative because they're in the opposite direction. So my resultant force is negative mu r, take away mg sine alpha, and that's equal to the mass, which is m, times the acceleration, which is negative 4/5 g. So I'm just going to now tidy this up. I'm going to substitute 4/5 mg in for r, and I'm going to substitute 3/5 in for sine alpha. So I get negative mu 4/5 mg, take away mg times 3/5 equals m times negative 4/5 g. So we've got mg in each of our terms there. So if we divide through by mg, they cancel out nicely. And I'm left with negative 4/5 mu, take away 3/5 equals negative 4/5. So my only unknown is mu. If I rearrange it, I get mu equals 1/4. So the answer to part A is that mu is equal to 1/4. Now, part B asks us to determine, it says the particle comes to rest at the point A on the plane. Determine whether the particle will remain at A, carefully justifying your answer. So I think at this point it's helpful to draw another diagram. So we've still got our rough inclined plane at angle alpha. The particle has gone up the plane and it's come to rest at this point, but its mass is still m. So this force is still here, and these components are the same, mg cos alpha and mg sine alpha. Our reaction force is still there, but we're trying to decide whether it stays at this point or whether it starts to go back down the plane. So now friction is acting in this direction. So it's holding it where it is, or it's acting against the direction of motion. So if we think about the two forces at play here, deciding whether it will remain at A, we're trying to weigh up whether this force acting up here is bigger or smaller than this force here, which is the only force pulling it back down the plane in this direction. So up the plane, we've got mu r. Down the plane, we've got mg sine alpha. Now r is 4/5 mg, and we've just found out that mu is 1/4. So 1/4 4/5 mg, and mg sine alpha is 3/5. So this 3/5 mg is bigger than this 4/20 mg. So the particle will not remain at A.